Imagine stepping outside on a summer afternoon. The temperature is high, but you've dealt with heat before. You find some shade, grab a bottle of water, and assume you'll be fine. After all, that's what we've always been told. Stay hydrated. Stay cool. Avoid direct sunlight. But what if none of that worked? What if there was a point where the human body simply lost the ability to cool itself? A point where drinking more water wouldn't save you. A point where even sitting motionless in the shade with a fan blowing directly at your face would only delay the inevitable. For decades, scientists believed this threshold was so extreme that it existed mostly in theory. A number on a chart. A limit that almost no place on Earth would ever reach. But recent research has revealed something deeply unsettling. That deadly boundary may be far closer than anyone expected. In fact, parts of the world have already come dangerously close. Some cities may have briefly crossed it. And as global temperatures continue to rise, conditions once considered nearly impossible could become a reality for hundreds of millions of people. This isn't a story about discomfort. It isn't about record-breaking temperatures or another ordinary heat wave. This is about the moment heat stops being survivable. The moment the laws of human biology collide with the limits of our planet. And the most shocking part? That future may be arriving much sooner than anyone imagined. When most people think about dangerous weather, they imagine hurricanes tearing apart coastlines, tornadoes ripping through neighborhoods, or floods swallowing entire towns. These disasters are dramatic. They leave visible destruction behind. News helicopters capture the damage from above, and the world watches in shock. Heat is different. Heat rarely destroys buildings. It doesn't leave debris scattered across the landscape. It arrives quietly, often beneath clear blue skies, and because of that, it is one of the most underestimated threats on Earth. Yet year after year, extreme heat kills more people than many other weather disasters combined. The strange part is that most people don't really understand why. Ask someone what makes a hot day dangerous, and they'll probably point to the temperature. If the thermometer reads 110 degrees Fahrenheit or 43 degrees Celsius, most people assume that's far more dangerous than a day in the low 90s. It seems obvious. Higher temperatures mean greater danger. But nature is not always that simple. In reality, some of the deadliest heat conditions on Earth occur at temperatures that many people would consider manageable. Meanwhile, some places regularly experience temperatures well above 110 degrees and remain surprisingly survivable. The difference comes down to a factor that most people ignore. Humidity. Humidity is invisible. You cannot see it hanging in the air. Yet it can completely transform the way the human body experiences heat. Nearly everyone has felt this without understanding the science behind it. Imagine two different summer afternoons. The first takes place in a desert. The temperature reaches 115 degrees Fahrenheit. The sun feels intense. The ground radiates heat. Yet when you step into the shade, the air feels noticeably better. A breeze provides relief. Your sweat dries almost instantly. Now imagine a second afternoon. The temperature is only 90 degrees Fahrenheit. On paper, it seems far less dangerous. But the air feels thick and heavy. Your clothes stick to your skin. Sweat drips down your face but never seems to evaporate. Even standing still feels exhausting. Most people would choose the second environment as the more comfortable one because the thermometer shows a lower number. Their bodies would disagree. In many cases, the humid 90-degree day is actually far more dangerous than the dry 115-degree day. That fact alone changes the entire conversation about extreme heat. For generations, people have focused almost exclusively on temperature records. Every summer brings headlines about the hottest day ever recorded in one city or another. But scientists studying human survival have learned that temperature by itself tells only part of the story. The real danger emerges when heat and humidity combine. Together, they create conditions that can overwhelm the body's natural cooling system. And when that system fails, survival becomes a race against time. For thousands of years, humanity has successfully adapted to some of the harshest environments on Earth. People have lived in deserts where daytime temperatures regularly exceed 120 degrees Fahrenheit. Communities have survived in tropical jungles where humidity remains high year-round. Entire civilizations have flourished in climates that would seem unbearable to outsiders. This long history of adaptation created a comforting assumption. Many people began to believe that humans could survive almost any level of heat as long as they had enough water and could find some shade. It sounds reasonable. After all, if you're hot, you drink water. If the sun is beating down, you move into the shade. If you're sweating heavily, you rest until you cool down. Those strategies work most of the time. But what scientists have discovered is deeply unsettling. There is a point where all of those survival strategies stop working. A point where water is no longer enough. A point where shade offers little protection. A point where the human body begins overheating even when a person is doing everything correctly. The frightening thing is that this threshold is not science fiction. It is not a distant future scenario. It is rooted in basic biology and physics. Every human being on Earth shares the same fundamental limitation. Our bodies generate heat constantly. Even when you're sitting quietly watching television, your cells are producing energy. That energy keeps your organs functioning, your muscles ready, and your brain active. The problem is that every bit of energy produced inside the body also creates heat. Under normal conditions, that heat escapes into the environment. But what happens when the environment becomes too hot? What happens when the air surrounding you becomes so warm and so humid that your body can no longer release the heat it produces? That question lies at the center of one of the most important scientific discoveries of the modern era. For decades, researchers assumed the answer existed safely beyond anything humans would experience in the real world. Then measurements began appearing in places scientists never expected. Cities across South Asia started recording combinations of heat and humidity that pushed closer and closer to the theoretical limits of human survival. Researchers studying weather data noticed something alarming. The margin between survivable conditions and unsurvivable conditions was shrinking. Events once considered nearly impossible were becoming more common. And some of the world's most densely populated regions were sitting directly in the path of this growing threat. What makes this danger particularly frightening is how ordinary it appears. A hurricane announces itself days in advance. A tornado siren screams through the night. Floodwaters rise visibly. Extreme humid heat often arrives disguised as an unpleasant summer day. People go to work. Children play outside. Families continue their routines. Meanwhile, the atmosphere is quietly moving closer to a threshold that the human body was never designed to endure. Most victims never see it coming. That's because the deadliest heat doesn't feel dramatic. It feels exhausting, oppressive, relentless. And by the time many people realize they're in danger, their bodies have already begun losing the battle. Scientists now believe this hidden threat could become one of the defining challenges of the 21st century. Not because the planet is becoming universally hotter, but because certain regions are becoming hotter and wetter at the same time. That combination changes everything. To understand why, we first need to understand the remarkable system that has allowed human beings to survive heat for hundreds of thousands of years. Because before we can understand how the body fails, we need to understand how it keeps us alive in the first place. At this very moment, your body is producing heat. You don't notice it because the process is happening constantly, every second of every day. Every cell inside your body is burning fuel to create energy. Your heart beats. Your lungs expand and contract. Your brain processes information. Your muscles maintain posture even when you're sitting perfectly still. All of these activities generate heat. In fact, a resting human body produces roughly the same amount of heat as an old-fashioned 100-watt light bulb. That might not sound like much. But imagine placing a light bulb inside a sealed box and leaving it there. Over time, the temperature inside that box would begin to rise. The heat has to go somewhere. The human body faces the same challenge. To stay alive, it must constantly remove excess heat from its core. And it must do so with incredible precision. Human beings operate within a remarkably narrow temperature range. The average core body temperature sits around 98.6 degrees Fahrenheit, or 37 degrees Celsius. Move too far below that point and hypothermia begins. Move too far above it and an entirely different danger emerges. The proteins that power every process in the body are sensitive to temperature. Organs function properly only within a specific range. The brain itself depends on stable conditions. Raise the body's core temperature by just a few degrees and serious problems begin to appear. Raise it further and those problems become life-threatening. That means your body is constantly performing a balancing act. Heat is being produced inside you. At the same time, heat must be released into the environment. As long as those two processes remain balanced, everything works perfectly. Most of the time, the body accomplishes this without any conscious effort. On a cool day, excess heat simply escapes into the surrounding air. Your skin is warmer than the environment around it, so heat naturally flows outward. The process is similar to placing a hot cup of coffee in a cool room. Over time, the coffee loses heat until it reaches the same temperature as its surroundings. The human body works in much the same way. But this simple system has a weakness. What happens when the air around you becomes nearly as warm as your skin? Or even hotter? Suddenly, the easy path for heat to escape begins to disappear. The body can no longer rely on temperature differences alone. That's when one of humanity's greatest evolutionary advantages takes over. Sweating. Most people think of sweat as an inconvenience. It ruins clothes. It drips into your eyes. It leaves you feeling sticky and uncomfortable. But from a biological perspective, sweating is one of the most extraordinary survival tools ever developed by a large animal. Without it, human civilization might never have existed. Millions of years ago, our ancestors evolved a cooling system unlike almost anything found elsewhere in the animal kingdom. While many animals depend primarily on panting or seeking shade, humans developed millions of specialized sweat glands spread across nearly the entire surface of the body. Today, the average person possesses between 2 and 4 million sweat glands. When the brain detects rising body temperatures, these glands activate automatically. Water is released onto the skin. At first glance, this seems strange. How can simply becoming wet cool the body? The answer lies in one of the most important processes in physics: evaporation. Water requires energy to transform from a liquid into a vapor. That energy has to come from somewhere. When sweat evaporates from your skin, it pulls heat away from your body. The heat that was trapped inside you becomes part of the energy used to turn liquid water into invisible vapor. The vapor drifts away. The heat goes with it. And your body cools down. It is an incredibly elegant system. In fact, it is so effective that humans can survive conditions that would overwhelm many larger animals. Under extreme circumstances, a healthy adult can produce more than a liter of sweat per hour. Some highly trained athletes can produce even more. Each drop represents a tiny packet of heat being removed from the body. Collectively, those millions of droplets create a powerful cooling engine. This ability helped humans spread into some of the hottest environments on Earth. It allowed hunters to move long distances beneath the African sun. It enabled workers to labor in harsh climates. It helped entire civilizations flourish where many other species would struggle. For hundreds of thousands of years, sweating served as humanity's secret weapon against heat. But every weapon has limitations. And hidden within this remarkable cooling system lies a vulnerability that most people never consider. Sweating only works if the sweat can evaporate. Read that sentence again. The cooling does not happen when sweat leaves your glands. The cooling happens when sweat leaves your skin. That distinction changes everything. Imagine stepping out of a swimming pool on a windy day. Even if the air temperature feels comfortable, you often feel chilly. That's because water covering your skin is evaporating rapidly. As it evaporates, it steals heat from your body. The faster the evaporation, the stronger the cooling effect. Now imagine wrapping yourself in plastic. The water can no longer evaporate efficiently. Instead, it remains trapped against your skin. Almost immediately, the cooling effect disappears. The same principle applies to sweat. If sweat evaporates quickly, your body's cooling system operates at full power. If evaporation slows down, cooling becomes less effective. And if evaporation stops altogether, the entire system begins to fail. This is where the story becomes truly important. Because the effectiveness of evaporation depends on something outside your body. The air itself. When the surrounding air is dry, evaporation happens easily. The air has plenty of capacity to absorb moisture. Sweat disappears quickly. Cooling remains efficient. But when the air is already loaded with moisture, everything changes. The atmosphere becomes less willing to accept additional water. Evaporation slows. Sweat remains on the skin. Your clothes become soaked. Your body works harder and harder to cool itself. Yet it achieves less and less success. The cooling engine is still running, but it is losing power. And if conditions continue worsening, the system approaches a point where it can no longer keep up. A point where heat begins accumulating inside the body faster than it can be removed. A point where survival becomes increasingly difficult. The human body is an extraordinary machine. It can adapt to deserts. It can endure tropical climates. It can survive temperatures that seem impossible. But every machine has limits. And understanding those limits requires us to examine the factor that turns ordinary heat into something far more dangerous. Not temperature alone. Not sunlight. Not even dehydration. The real threat comes from the invisible partnership between heat and humidity. And once those two forces combine in exactly the wrong way, the body's greatest cooling system begins to break down. If you've ever traveled between different climates during the summer, you've probably noticed something strange. Two places can have completely different temperatures, yet the cooler place somehow feels far more uncomfortable. Someone visiting Arizona might step outside into temperatures above 110 degrees Fahrenheit and be shocked by the heat. Yet after moving into the shade, they often discover that the environment feels surprisingly manageable. Then they travel to a place like Florida, Louisiana, or the Gulf Coast. The thermometer reads only 90 degrees. Yet within minutes, they feel exhausted. Their shirt becomes soaked. Sweat pours from their skin. The air feels thick and heavy. Many people describe it as feeling like they're breathing through a wet blanket. The obvious question is why? Why can 115 degrees sometimes feel easier to tolerate than 90? The answer lies in the difference between dry heat and humid heat. And understanding that difference is the key to understanding why extreme heat can eventually become unlivable. Let's start with the desert. Deserts are famous for their extreme temperatures. Places like Death Valley, Phoenix, and parts of the Middle East routinely experience temperatures that seem almost impossible. The ground becomes hot enough to burn skin. Cars overheat. Road surfaces soften. Everything exposed to the sun feels like it's inside an oven. Yet despite these extreme temperatures, deserts possess one critical advantage. The air is dry. Very dry. That dryness allows the human body's cooling system to operate at maximum efficiency. Remember what we learned in the previous section. Sweat cools the body only when it evaporates. In a desert environment, the surrounding air contains very little moisture. The atmosphere is thirsty. It eagerly absorbs water from your skin. As a result, sweat evaporates almost instantly. The body's natural cooling system works exactly as intended. This doesn't mean desert heat is safe. Far from it. People still die from dehydration, heat exhaustion, and heat stroke in dry climates. But the body's radiator remains operational. As long as enough water is available and a person can escape direct sunlight when necessary, there is still a pathway for heat to leave the body. Now compare that with humid environments. Unlike deserts, humid regions contain large amounts of water vapor already suspended in the air. The atmosphere is no longer thirsty. Instead, it is already carrying a heavy load of moisture. And that's where the problem begins. Imagine trying to pour more water into a glass that's already full. Eventually, the glass simply can't hold any more. The same thing happens with humid air. As moisture levels increase, the atmosphere becomes less willing to accept additional water from your skin. Evaporation slows down. Sweat begins accumulating. Instead of disappearing into the air, it remains on your body. Your clothes become damp. Your skin feels sticky. You sweat harder and harder. Yet you feel less and less relief. At first, this is merely uncomfortable. But as humidity continues increasing, the consequences become much more serious. Because the body's cooling system depends entirely on evaporation. When evaporation slows, cooling slows. When evaporation nearly stops, cooling nearly stops. And when cooling stops, the body begins storing heat. This is why humidity transforms heat from an inconvenience into a threat. Most people focus on how hot the air feels. Scientists focus on how effectively the body can cool itself within that air. Those are not always the same thing. A person standing in a desert at 110 degrees may actually be shedding heat more effectively than someone standing in a humid environment at 90 degrees. The thermometer doesn't tell the whole story. The atmosphere's ability to absorb moisture matters just as much, perhaps even more. Meteorologists often use a measurement called the heat index to estimate how hot conditions feel to the average person. The heat index combines temperature and humidity into a single number. When humidity rises, the heat index rises too. That's why a temperature of 90 degrees can feel like 105 degrees or even higher under extremely humid conditions. But even the heat index doesn't fully capture the danger. Because what truly matters isn't how hot conditions feel. What matters is whether the human body can continue removing heat. And that depends on evaporation. Imagine spending an afternoon outside on a humid summer day. At first, you simply feel uncomfortable. Sweat forms on your forehead. Your clothing sticks to your skin. You feel sluggish. A little later, fatigue begins setting in. Tasks that normally feel easy suddenly require more effort. Your heart works harder. Your breathing becomes heavier. The body is increasing its attempts to cool itself. More blood is being pushed toward the skin. More sweat is being produced. More energy is being spent fighting the heat. Yet because humidity is limiting evaporation, much of that effort is wasted. It's like pressing harder on a car's accelerator while driving through deep mud. The engine works harder, but the results become increasingly disappointing. Eventually, if conditions become severe enough, the body's cooling system falls behind. Heat begins accumulating faster than it can be removed. Core temperature starts rising. And that's when the situation becomes dangerous. The frightening thing is that many people don't recognize the danger until it's already happening. Because humid heat doesn't always feel dramatic. A dry desert often feels more intimidating. The temperatures look more impressive. The environment appears more hostile. Humid heat hides behind ordinary summer weather. People see clouds, green trees, lush vegetation, a lower temperature on the thermometer. Everything appears less threatening. Yet beneath the surface, physics is quietly working against them. This is why some of the most dangerous places on Earth are not deserts at all. They're coastal regions, river valleys, tropical cities. Places where heat and moisture combine into a particularly dangerous mixture. Scientists sometimes describe this combination as creating an atmosphere that slowly suffocates the body's cooling system. The hotter and wetter the air becomes, the less effective sweating becomes. And the less effective sweating becomes, the closer a person moves toward a biological limit that humanity cannot overcome. A limit that exists regardless of fitness, regardless of determination, regardless of experience. For most of human history, conditions approaching that limit were extremely rare. Nature simply didn't produce them very often. But that is beginning to change. As the planet warms, the atmosphere becomes capable of holding more moisture. Warmer oceans release more water vapor. Humid regions become even more humid. And the dangerous partnership between heat and moisture grows stronger. Which brings us to one of the most important numbers in climate science. A measurement specifically designed to determine whether the human body can survive a given combination of heat and humidity. A number so important that scientists use it to identify the exact point where the body's cooling system begins to fail. A number known as the wet bulb temperature. And once you understand what that number represents, you'll understand why researchers around the world are becoming increasingly alarmed. For most of human history, people judged heat using a simple measurement. Temperature. If the thermometer showed 80 degrees, it felt comfortable. If it showed 100 degrees, it felt hot. If it climbed above 110 degrees, people knew conditions were becoming dangerous. Simple. Or at least it seemed simple. The problem is that the thermometer only tells part of the story. It tells you how hot the air is. It does not tell you how effectively your body can survive in that air. And those are two very different things. Imagine two cities. In the first city, the temperature is 115 degrees Fahrenheit, but the air is extremely dry. In the second city, The temperature is only 90 degrees Fahrenheit, but the humidity is overwhelming. Which city is more dangerous? Most people immediately choose the first one. Scientists often choose the second. That answer surprises people because it challenges everything they think they know about heat. But it also reveals why researchers needed a better way to measure danger. They needed a number that combined both temperature and humidity into a single measurement. A number that reflected not how hot the air felt, but whether the human body could actually survive in it. That search led scientists to one of the most important concepts in climate science: wet bulb temperature. The name sounds technical and intimidating, but the idea behind it is surprisingly simple. Imagine taking a normal thermometer. Now wrap a wet cloth around the bulb at the bottom. Next, place that thermometer in moving air. Something interesting happens. As water evaporates from the cloth, it cools the thermometer. The faster the evaporation, the cooler the reading becomes. If the air is very dry, evaporation happens rapidly. The thermometer becomes significantly cooler than the actual air temperature. If the air is humid, evaporation slows down. The thermometer remains much warmer. In extremely humid conditions, evaporation becomes so limited that the wet bulb temperature rises close to the actual air temperature. This simple experiment reveals something profound. The wet cloth behaves almost exactly like human skin. Just as sweat evaporates from your body, water evaporates from the cloth. Just as evaporation cools your skin, it cools the thermometer. The wet bulb thermometer is essentially a model of the human body's cooling system. And that makes it incredibly valuable. Because instead of measuring air temperature alone, wet bulb temperature measures how effectively evaporation can cool a surface. In other words, it measures how effectively your body can cool itself. The lower the wet bulb temperature, the easier it is for sweat to evaporate. The higher the wet bulb temperature, the harder it becomes. And as that number continues rising, the body's natural cooling system begins losing its ability to function. This is where the science becomes truly unsettling. For decades, researchers believed there was a specific wet bulb temperature that represented the absolute limit of human survival. That number was 35 degrees Celsius, or about 95 degrees Fahrenheit. At first glance, 95 degrees might not sound particularly terrifying. Many places regularly experience temperatures above that level. But remember, wet bulb temperature is not the same thing as ordinary temperature. A wet bulb reading of 95 degrees represents a combination of heat and humidity so extreme that it approaches the limits of human biology. Scientists arrived at this number through physics. The logic seemed straightforward. Human skin temperature during heavy sweating typically sits around 35 degrees Celsius. If the wet bulb temperature of the surrounding air also reaches 35 degrees, then the temperature difference between the body and the environment essentially disappears. Without that difference, heat can no longer escape effectively. The body loses its ability to cool itself. From that point forward, internal heat begins accumulating. Core temperature rises. Eventually, survival becomes impossible. Even if a person is sitting motionless. Even if they are drinking unlimited water. Even if they are sheltered from direct sunlight. The body simply cannot shed heat fast enough. Physics takes over. For years, this 35-degree threshold became one of the most important numbers in climate science. It represented the theoretical edge of human survivability. Fortunately, researchers believed there was still a substantial safety margin. Historically, wet bulb temperatures rarely approached that level. Even in some of the hottest and most humid regions on Earth, measurements generally remained several degrees below the danger threshold. That seemed reassuring. Humanity appeared to have a buffer. A gap between the worst conditions nature could produce and the point where survival became impossible. But then scientists began looking toward the future. As global temperatures increased, climate models suggested that some regions could eventually experience much higher wet bulb temperatures. Areas already known for oppressive humidity appeared especially vulnerable. South Asia, the Persian Gulf, parts of China, sections of the United States. Researchers realized that continued warming could push certain locations closer and closer to the theoretical limit. Suddenly, wet bulb temperature was no longer just an academic concept. It became a practical concern. a way of identifying places where future heat might become genuinely dangerous. The more scientists studied the issue, the more attention the number received. News articles referenced it. Climate reports discussed it. Researchers built entire projections around it. The 35-degree threshold became a symbol of the line separating survivable heat from unsurvivable heat. Yet there was one important problem. Despite all the confidence surrounding the number, it remained largely theoretical. It was based on calculations, physics, models, reasonable assumptions. But assumptions nonetheless. No one had actually tested the limit on real human beings. No one had placed healthy volunteers into carefully controlled environments and measured exactly when their bodies lost the ability to regulate temperature. The famous 35-degree threshold existed mostly on paper. And that raised an uncomfortable question. What if the real limit was different? What if the human body failed before reaching 35 degrees? What if the safety margin scientists believed existed was smaller than anyone realized? Those questions remained unanswered for years. Then researchers decided to find out. They designed experiments unlike anything attempted before. Experiments that would place real people inside environmental chambers. Experiments that would monitor core body temperature in real time. Experiments designed to identify the exact moment the human body stopped winning its battle against heat. The results would shock the scientific community. Because when researchers finally tested human beings instead of relying solely on theory, they discovered something alarming. The real limit wasn't where they thought it was. It was lower. And that single discovery changed everything. For decades, the number seemed settled. 35 degrees Celsius. 95 degrees Fahrenheit. That was the wet bulb temperature scientists believed represented the ultimate limit of human survival. It appeared in research papers. It appeared in climate models. It appeared in countless discussions about the future of extreme heat. The threshold was treated almost like a law of nature. If conditions remained below that point, survival should theoretically be possible. If conditions exceeded it, survival would become impossible. Simple. But science has a habit of challenging its own assumptions. And eventually, a group of researchers asked an important question. What if the famous 35-degree limit wasn't actually correct? What if the human body began failing long before reaching that threshold? The only way to find out was to move beyond theory and conduct real-world experiments. That challenge fell to researchers at Pennsylvania State University. Their goal was ambitious. They wanted to determine the true limits of human heat tolerance. Not through equations, not through computer models, but through direct observation of living people. To accomplish this, they built highly controlled environmental chambers capable of recreating a wide variety of temperature and humidity conditions. Inside these chambers, researchers could carefully manipulate the atmosphere. They could increase temperatures, raise humidity levels, control airflow, and monitor exactly how the human body responded. Healthy young volunteers were recruited to participate. These individuals were not running marathons or performing intense physical labor. Instead, they engaged in light, everyday activities similar to what many people do at home. Reading, cooking, walking slowly. Basic tasks requiring minimal effort. The reason was simple. Scientists wanted to understand the limits of ordinary survival. Not athletic performance. Not military endurance. Just the conditions under which a healthy person could no longer maintain a safe body temperature. Each volunteer swallowed a small telemetry capsule. This device continuously measured core body temperature from inside the body. Researchers then exposed participants to gradually worsening combinations of heat and humidity. As conditions intensified, scientists watched carefully. At first, the body responded normally. Sweating increased. Blood flow shifted toward the skin. The body's cooling systems worked exactly as expected. But eventually, something changed. A critical point appeared. Researchers called it the environmental critical limit. This was the moment when the body's core temperature stopped remaining stable. Instead of holding steady, it began rising continuously. That distinction was crucial. Once core temperature starts climbing without stabilizing, the body is effectively losing the battle against heat. Even if the increase is slow, the direction matters. The cooling system can no longer keep pace. Heat begins accumulating. And over time, that accumulation becomes dangerous. When researchers analyzed the results, they discovered something startling. The critical limits appeared well below the famous 35-degree wet bulb threshold. In many cases, dangerous conditions emerged around wet bulb temperatures closer to 31 degrees Celsius. That's roughly 88 degrees Fahrenheit. The difference may not sound dramatic, but scientifically, it was enormous. For decades, researchers had assumed humanity possessed a larger safety buffer. The experiments suggested that buffer might be much smaller. The implications were profound. If the real limit was closer to 31 degrees instead of 35 degrees, then dangerous conditions could occur far sooner than expected. Places previously considered safely below the survival threshold suddenly appeared much closer to it. The margin between safety and danger had narrowed significantly. The findings spread quickly throughout the scientific community. Researchers began re-evaluating earlier assumptions. Climate projections were examined with fresh eyes. Heat risk assessments became more urgent. The conversation had changed. But why exactly was the lower threshold so important? The answer lies in the difference between theoretical survival and practical survival. The original 35-degree figure represented an idealized limit. It assumed a healthy person, perfect hydration, minimal physical activity, optimal conditions. Essentially, it described the edge of what human biology might tolerate under the best possible circumstances. Real life is rarely ideal. People get tired. They become dehydrated. They perform physical work. They have medical conditions. They are elderly. They are children. They experience stress. All of these factors reduce heat tolerance. The Penn State experiments revealed that the body begins struggling before reaching the theoretical maximum. Long before complete failure occurs, the cooling system starts losing effectiveness. Core temperatures begin creeping upward. The danger starts earlier than expected. And that realization was deeply concerning. Because many regions of the world are already experiencing conditions approaching these lower thresholds. Not every year. Not every day. But often enough to attract attention. Scientists began examining weather records more closely. What they found was troubling. Extreme heat and humidity events once considered rare were appearing with increasing frequency. Some locations were recording combinations of temperature and moisture that approached the newly identified danger zone. The trend was especially noticeable in coastal regions and densely populated tropical areas. Places where millions of people live. Places where power outages can leave entire communities without air conditioning. Places where even a brief period of extreme conditions can place enormous stress on public health systems. The experiments also highlighted another uncomfortable reality. The human body does not suddenly collapse at a specific number. Heat illness exists on a spectrum. As conditions worsen, risks increase gradually. Heat exhaustion develops. Cognitive performance declines. Decision-making becomes impaired. Physical abilities weaken. The body becomes progressively less capable of protecting itself. By the time the absolute limit is reached, the situation has already become extremely dangerous. This means the story is not simply about one magic number. It's about the shrinking distance between ordinary summer conditions and temperatures capable of overwhelming human physiology. And that distance is becoming increasingly important as the climate changes. The atmosphere today is not the same atmosphere that existed a century ago. Warmer air holds more moisture. Oceans are transferring more water vapor into the atmosphere. Heat waves are becoming more intense in many regions. The exact combination scientists fear most, heat plus humidity, is becoming easier to produce. That's why researchers no longer view wet bulb temperature as an obscure scientific measurement. It has become one of the most important indicators of future climate risk. Because it measures something far more meaningful than temperature alone. It measures whether the human body can continue functioning in the environment around it. And according to the experiments, that limit may be closer than humanity ever realized. The troubling question now is no longer whether dangerous combinations of heat and humidity can occur. The question is how often they will occur in the future. And unfortunately, History already provides several disturbing clues about what happens when entire populations are exposed to extreme heat. For many people, extreme heat still feels like a future problem. Something scientists warn about. Something climate models predict. Something that might happen decades from now. But the truth is far more unsettling. The consequences of extreme heat are not waiting in the future. They are already here. In fact, some of the deadliest weather disasters of the modern era were not hurricanes, floods, or tornadoes. They were heat waves. And unlike most natural disasters, many of them unfolded beneath clear skies. No violent winds. No collapsing buildings. No dramatic images broadcast around the world. Just heat. Relentless, invisible heat. The kind that quietly overwhelms the human body until survival becomes impossible. One of the first events to truly shock scientists occurred in Europe during the summer of 2003. At the time, Europe was not considered one of the world's most heat-vulnerable regions. Many people associated deadly heat with deserts or tropical climates. Europe seemed relatively safe. Then the heat wave arrived. Day after day, temperatures climbed far above normal levels. Cities baked beneath an unrelenting sun. Nighttime brought little relief. Buildings absorbed heat throughout the day and slowly released it after sunset. Millions of people struggled to cool down. Hospitals began filling. Emergency services became overwhelmed. Morgues ran out of space. By the time the heat wave ended, researchers estimated that more than 70,000 people had died across the continent. The scale of the tragedy stunned the world. Many victims were elderly individuals living alone. Others lacked access to effective cooling. Some simply underestimated the danger. The event forced scientists to reconsider how deadly heat could become even in wealthy, developed societies. The disaster also exposed a critical weakness. Human beings depend heavily on nighttime cooling. Normally, temperatures drop after sunset, allowing buildings, streets, and people to release accumulated heat. But during the European heat wave, nights remained unusually warm. The body never received a chance to recover. Stress accumulated day after day. The heat wave became a turning point in climate research. Scientists realized that heat did not need to reach theoretical survival limits to become catastrophic. Long-duration exposure could be just as deadly. Yet Europe 2003 was only the beginning. 7 years later, another devastating event struck Russia. The summer of 2010 brought extraordinary heat to western Russia, including the region surrounding Moscow. Temperatures shattered records. Drought intensified. Wildfires erupted across the landscape. Smoke blanketed cities. Visibility collapsed. Millions of people found themselves trapped between extreme heat and choking air pollution. Hospitals once again struggled to cope. Health systems came under enormous pressure. Researchers later estimated that tens of thousands of excess deaths occurred during the disaster. The event demonstrated how heat often triggers secondary crises. Wildfires, air pollution, infrastructure strain, agricultural losses. Heat rarely acts alone. Instead, it amplifies other vulnerabilities already present within society. As temperatures rise, those vulnerabilities multiply. Then came another warning. One that shocked scientists because of where it occurred. The Pacific Northwest. For generations, cities like Seattle and Portland were known for mild weather. Residents rarely worried about extreme heat. Many homes lacked air conditioning entirely. It simply wasn't considered necessary. Then, during the summer of 2021, an extraordinary atmospheric event developed. Meteorologists called it a heat dome, a massive region of high-pressure trapped heat near the surface. Temperatures climbed to levels few people thought possible. Some locations exceeded 120 degrees Fahrenheit. Entire communities found themselves facing conditions they had never experienced before. Roads buckled. Power systems struggled. Schools closed. Emergency rooms filled with heat-related patients. Hundreds of people died. Scientists were stunned, not only because of the temperatures themselves, but because the event occurred in a region historically considered low risk. The disaster highlighted a dangerous reality. Communities are often most vulnerable where extreme heat is unexpected. People prepare for threats they know. They struggle with threats they don't anticipate. The Pacific Northwest had little experience dealing with such temperatures. Its infrastructure reflected that reality. Many buildings were designed to retain warmth during cool winters. Few homes possessed effective cooling systems. When the heat arrived, millions of people had limited protection. The tragedy revealed how quickly vulnerability can emerge when weather exceeds historical expectations. Yet perhaps the most important lesson from these disasters is what they tell us about the limits of human survival. None of these heat waves officially reached the famous 35-degree wet bulb threshold. Most remained well below it. And yet thousands upon thousands of people still died. Why? Because the theoretical survival limit is not the same thing as a safe environment. Human beings suffer long before reaching absolute physiological limits. Elderly individuals possess reduced heat tolerance. Children regulate temperature differently. People with heart disease face greater risks. Medications can interfere with sweating. Dehydration develops rapidly. Physical labor increases internal heat production. Every one of these factors narrows the gap between survivable and deadly conditions. The result is a sobering reality. A city does not need to cross the ultimate threshold of human survival to experience a public health catastrophe. Danger begins much earlier. That understanding has become increasingly important as researchers analyze recent trends. Around the world, heat waves are becoming more frequent, more intense, longer lasting. Records that once seemed extraordinary are being broken repeatedly. Each new event provides scientists with additional data. And much of that data points in the same direction. The atmosphere is changing. The combinations of heat and humidity that concern researchers are appearing more often. In many cases, they are appearing in regions containing millions of people. That realization has transformed how scientists view extreme heat. It is no longer simply a weather event. It is a growing challenge to public health, infrastructure, and human survivability itself. But among all the disasters studied by researchers, one event stands out for a particularly disturbing reason. Because unlike Europe or Russia, it occurred in a city already familiar with extreme heat. A city where people believed they understood how to survive high temperatures. Yet when a deadly combination of heat, humidity, and infrastructure failure struck, the results were devastating. The city was Karachi. And what happened there would become one of the clearest warnings yet about the future of unlivable heat. On June 18, 2015, the city of Karachi woke up to what seemed like another brutally hot summer day. For the more than 20 million people living in Pakistan's largest city, extreme heat was nothing new. Every year, residents endured scorching temperatures, crowded streets, and long summer months that pushed both people and infrastructure to their limits. Most assumed this heat wave would be no different. They were wrong. As the day progressed, temperatures climbed toward 45 degrees Celsius, or 113 degrees Fahrenheit. But temperature alone wasn't the real problem. Humidity from the nearby Arabian Sea filled the atmosphere. The air felt heavy, oppressive. Every breath seemed harder than the last. Sweat covered people's skin, but much of it failed to evaporate efficiently. The body's natural cooling system was beginning to struggle. Few people understood just how dangerous the situation had become. What made the disaster especially deadly was the timing. The heat wave struck during the holy month of Ramadan. Many people were fasting throughout the day, abstaining from food and water from sunrise until sunset. As temperatures soared, dehydration spread rapidly through the population. The human body was already fighting extreme environmental stress. Now many people lacked one of its most important defenses: the ability to replace lost fluids. Hospitals soon began noticing a surge in emergency cases. Patients arrived suffering from heat exhaustion. Others showed signs of severe dehydration. Many were already slipping into heat stroke. Doctors and nurses worked around the clock. But the number of patients kept growing. Then another problem emerged: electricity failures. Parts of Karachi experienced rolling blackouts as demand for power surged. Air conditioners stopped working. Fans shut down. Water pumps failed. Entire neighborhoods suddenly lost the very tools people depended on to survive extreme heat. Inside apartments and homes, temperatures continued climbing. Many residents found themselves trapped in buildings that acted like giant ovens. The heat that entered during the day remained trapped inside. Night offered little relief. Normally, cooler evening temperatures allow the body to recover from daytime stress. But during the Karachi heat wave, nights remained unusually warm. People who had spent all day fighting the heat were forced to continue fighting through the darkness. Hour after hour, day after day, the human body can withstand incredible stress for short periods. What it struggles to survive is continuous stress without recovery. That is exactly what happened in Karachi. Emergency rooms became overwhelmed. Stretchers filled hallways. Doctors ran out of available beds. Medical staff reported scenes unlike anything they had experienced before. Patients arrived faster than hospitals could treat them. Refrigerated morgues reached capacity. Additional storage facilities had to be arranged. Families searched desperately for loved ones. Funeral services operated continuously. The scale of the tragedy became impossible to ignore. As the death toll climbed, the city entered crisis mode. Authorities established emergency relief centers. Volunteers distributed water. Aid organizations opened cooling stations. Military personnel assisted with response efforts. But the heat continued, and so did the deaths. By the time the heat wave finally weakened, estimates suggested that more than 1,200 people had lost their lives. Some estimates placed the number significantly higher. The exact total remains debated. What is not debated is the severity of the disaster. Karachi had experienced one of the deadliest heat waves in modern history. For climate scientists, however, the tragedy raised a critical question. How close had conditions come to the limits of human survival? Researchers began examining weather records in detail. Temperature data, humidity measurements, atmospheric conditions, hour by hour, day by day. What they discovered attracted global attention. The combination of heat and humidity had produced conditions approaching levels that scientists had long considered extremely dangerous. Not necessarily beyond the theoretical limit, but alarmingly close. Closer than many researchers expected to see in a major city. Karachi became a warning. A real-world example of what happens when extreme heat collides with dense populations, aging infrastructure, limited cooling access, and social vulnerability. The disaster also revealed something important about the future. Heat-related deaths are rarely caused by a single factor. Instead, they emerge from a chain reaction. The atmosphere becomes hotter. Humidity increases. Power demand surges. Electrical systems fail. Access to cooling disappears. Hospitals become overwhelmed. Water supplies come under stress. Small problems combine into a larger crisis. Scientists call this a compound disaster, and it represents one of the greatest concerns surrounding future heat waves. Because climate change doesn't operate in isolation. It interacts with existing weaknesses in society. Cities grow larger. Power grids face greater demand. Urban areas trap more heat. Populations become more concentrated. Every one of these trends increases vulnerability. Karachi demonstrated how quickly conditions can spiral when multiple stresses occur simultaneously. The city was not unprepared for heat. Its residents had lived with hot summers for generations. Yet even that experience proved insufficient when conditions became extreme enough. That realization sent a powerful message to researchers around the world. If a city accustomed to high temperatures could suffer such devastating losses, what would happen elsewhere as heat and humidity continue increasing? What would happen in regions with even larger populations? What would happen if similar conditions lasted longer, or occurred more frequently? Those questions are no longer theoretical, because the climate system is changing. And according to many projections, events resembling Karachi's deadly heat wave could become increasingly common during the coming decades. The frightening reality is that Karachi may not represent the worst-case scenario. It may represent an early warning, a glimpse of conditions that could affect far more people in the future. Which brings us to the question scientists are now racing to answer. As the planet continues warming, which regions are most at risk? Where could dangerous combinations of heat and humidity become common? And could parts of the world eventually experience conditions that move beyond the limits of human survivability altogether? The answers are forcing researchers to redraw the future map of where humanity can safely live. For most of human history, the question of where people could live was determined by familiar challenges. Access to water, fertile land, natural resources, protection from conflict. Extreme heat was certainly a factor, but it rarely defined the absolute limits of human settlement. People adapted. Communities developed ways to survive hot climates. Architecture evolved. Work schedules changed. Entire cultures learned how to live alongside intense summer temperatures. But climate scientists are now studying a possibility that goes beyond adaptation. A possibility that forces an uncomfortable question. What happens when some regions become so hot and humid that the human body itself becomes the limiting factor? Not agriculture. Not economics. Not politics. Human biology. To answer that question, researchers have spent years analyzing climate projections, atmospheric trends, and future warming scenarios. The results paint a troubling picture. As global temperatures rise, the atmosphere becomes capable of holding more water vapor. This relationship is one of the most fundamental laws in climate science. Warmer air can hold more moisture. Roughly 7% more moisture for every degree Celsius of warming. That may sound insignificant, but across an entire planet, it changes everything. More moisture means higher humidity. Higher humidity means less efficient evaporation. Less efficient evaporation means greater stress on the human body's cooling system. The same process that makes a humid summer day feel uncomfortable today could make future heat waves dramatically more dangerous. Scientists often describe this as a multiplier effect. Temperature rises. Humidity rises alongside it. The danger increases faster than either factor alone. And nowhere is this trend more concerning than in parts of South Asia. Countries like Pakistan, India, and Bangladesh already experience some of the most challenging heat and humidity combinations on Earth. Hundreds of millions of people live in regions where summer temperatures regularly climb above 40 degrees Celsius. Many communities depend on outdoor labor, agriculture, construction, transportation, work that exposes people directly to environmental conditions. Climate models suggest these regions could face some of the highest future wet bulb temperatures ever observed. Even small increases in average temperatures could significantly increase the frequency of dangerous heat events. What was once rare could become common. What was once considered extreme could become normal. And what is considered dangerous today could become routine. The concern extends far beyond South Asia. The Persian Gulf region also appears particularly vulnerable. Cities located along warm coastlines already experience extraordinary humidity levels during summer months. The surrounding waters act as massive sources of atmospheric moisture. As ocean temperatures rise, the atmosphere absorbs even more water vapor. Researchers have identified parts of the Gulf as locations where some of the world's highest future wet bulb temperatures may occur. Several climate studies suggest that certain coastal areas could periodically approach or even exceed thresholds once considered nearly impossible. For scientists, these projections serve as warnings. Not predictions of constant conditions, but indications of increasing risk and increasing frequency. China faces similar challenges, especially within densely populated eastern and southern regions. These areas combine large populations with hot summers and significant humidity. Millions of people already experience intense heat stress during peak summer months. Future warming could place additional pressure on both public health systems and infrastructure. Yet perhaps the biggest surprise in many climate projections is the United States. When people imagine dangerous humid heat, they often picture tropical regions. Few immediately think of North America, but scientists do, particularly when examining the southeastern United States. States along the Gulf Coast and portions of the eastern seaboard already experience high humidity levels. Warm ocean waters feed moisture into the atmosphere. Summer heat waves periodically push temperatures to dangerous levels. As warming continues, these conditions could become more severe. The concern isn't simply hotter temperatures. It's the combination of heat and humidity occurring together. That combination is what drives wet bulb temperatures upward. And that combination is what threatens the body's ability to cool itself. Some researchers describe future heat risk using a simple concept: days beyond human comfort. Historically, many regions experienced only a limited number of such days each year. Future projections suggest that number could rise dramatically. Weeks may become months. Occasional events may become seasonal patterns. The implications extend far beyond physical discomfort. Public health systems would face increasing pressure. Energy demand would surge. Water consumption would rise. Agricultural productivity could decline. Outdoor labor would become more difficult. Economic losses could reach enormous levels. Entire societies would need to adapt. And adaptation itself comes with limits. Air conditioning is often presented as the solution. In many situations, it is. Modern cooling technology has saved countless lives. But air conditioning depends on electricity. Electricity depends on infrastructure. Infrastructure depends on stability. During major heat waves, demand often rises precisely when systems are under the greatest stress. Power failures become more likely. And when cooling disappears, vulnerability rises immediately. This creates a troubling feedback loop. The hotter conditions become, the more people depend on cooling. The more people depend on cooling, the greater the pressure on power systems. The greater the pressure on power systems, the greater the consequences if failures occur. Scientists increasingly view this as one of the defining challenges of future heat resilience. Not simply surviving heat, but maintaining the systems required to survive it. The scale of the challenge becomes even clearer when population growth is considered. Many of the regions facing the highest projected heat stress are also among the most densely populated areas on Earth. Billions of people live within zones that could experience increasing heat risk throughout the coming decades. Not all of those regions will become unlivable. Not all projections will occur exactly as expected. Climate science involves uncertainty, but the overall trend is difficult to ignore. The world is warming. Humidity is increasing in many vulnerable regions. Extreme heat events are becoming more frequent, and the boundary between survivable and unsurvivable conditions is attracting growing scientific attention. Perhaps the most important lesson is that unlivable heat is not a distant science fiction concept. It is not something reserved for the end of the century. The warning signs are already visible today. The question is not whether dangerous heat will occur. The question is how prepared societies will be when it does. Because if recent history has taught scientists anything, it is that the future of extreme heat will not be determined solely by temperature. It will be determined by whether humanity can adapt quickly enough to stay ahead of its own biological limits. And that challenge may become one of the most important survival tests of the 21st century. By now, the pattern should be clear. Extreme heat is not simply about temperature. It is about the relationship between the human body and the environment surrounding it. As temperatures rise and humidity increases, the body's natural cooling system becomes less effective. Sweat evaporates more slowly. Heat escapes less efficiently. The margin between safety and danger begins to shrink. And eventually, under the most extreme conditions, survival may depend on something humanity did not possess for most of its history: artificial cooling. For thousands of years, people survived heat using methods that seem remarkably simple today. They built thick stone walls that blocked sunlight. They designed narrow streets that created shade. They worked during cooler hours and rested during the hottest parts of the day. They relied on breezes, water, and clever architecture. These strategies were often effective because the environment still allowed the body to cool itself. Even when temperatures were uncomfortable, evaporation continued working. The body's natural defenses remained functional. But as scientists have learned, there are conditions where those traditional strategies become insufficient. A person can sit in complete shade, drink plenty of water, avoid physical activity, and still face increasing danger. The reason is simple. None of those strategies directly reduce the temperature of the surrounding air. They help the body cope. They do not change the environment itself. And when environmental conditions approach the limits of human survivability, coping is no longer enough. The air itself must be cooled. That is where air conditioning becomes far more than a convenience. It becomes a survival technology. In many parts of the world, air conditioning is often viewed as a luxury, something associated with comfort, a way to escape an unpleasant summer afternoon. But during severe heat waves, air conditioning serves a completely different purpose. It creates an artificial environment where the human body can recover. It lowers air temperature. It reduces heat stress. Most importantly, it restores the body's ability to release excess heat. A cool room can mean the difference between survival and death. This reality has transformed how public health officials view extreme heat. Cooling centers are now considered essential emergency infrastructure. Cities establish air-conditioned shelters during heat waves. Schools, community centers, libraries, and public buildings are open to vulnerable residents. The goal is simple: provide safe environments before heat-related illness develops. Because once severe heat stroke begins, survival becomes much more difficult. Yet dependence on artificial cooling introduces a new vulnerability: electricity. Every air conditioner depends on power, and power grids face their greatest stress during extreme heat events. When temperatures soar, millions of people switch on air conditioners simultaneously. Demand rises rapidly. Transmission systems become overloaded. Equipment operates under intense strain. The risk of outages increases. This creates a dangerous paradox. The hotter conditions become, the more society depends on electricity. But the greater that dependence becomes, the more severe the consequences of failure. Scientists and engineers worry about this constantly, because history has shown what happens when cooling disappears during major heat waves. A blackout during mild weather is inconvenient. A blackout during extreme heat can become a public health emergency. Within hours, indoor temperatures begin climbing. Apartments trap heat. High-rise buildings become difficult to ventilate. Vulnerable populations lose access to their primary defense against dangerous conditions. The situation becomes even worse when heat combines with other disasters. Imagine a powerful hurricane striking a coastal region. Strong winds damage electrical infrastructure. Millions lose power. Normally, recovery efforts focus on restoring electricity as quickly as possible. But what happens if an extreme heat wave follows immediately afterward? Suddenly, communities face two emergencies at the same time: damaged infrastructure and dangerous heat. Researchers increasingly view these compound disasters as one of the greatest future risks. Because climate systems do not operate in isolation. Heat waves can overlap with droughts. Storms can disrupt power during hot weather. Wildfires can damage transmission lines. Each event amplifies the others. And as the climate continues changing, these overlapping crises may become more common. Urban areas face additional challenges. Cities absorb and store enormous amounts of heat. Concrete, asphalt, steel, and glass collect solar energy throughout the day. After sunset, that stored heat is slowly released back into the environment. This phenomenon is known as the urban heat island effect. In some cities, nighttime temperatures remain several degrees warmer than surrounding rural areas. That difference may not sound significant, but during a prolonged heat wave, it can have life-or-death consequences. Remember the lessons from previous disasters. The body needs nighttime recovery. When nights remain hot, stress accumulates. The cardiovascular system works harder. Sleep quality declines. The body's ability to recover weakens. Day after day, the burden grows. Urban heat islands intensify that burden, which means some of the world's largest cities may face disproportionate risks as temperatures continue rising. This is why scientists increasingly emphasize preparedness rather than panic. The future is not predetermined. Heat-related deaths are not unavoidable. Many of the most effective solutions already exist. Improved building design, expanded cooling infrastructure, more resilient power grids, urban tree planting, reflective roofing materials, early warning systems, public education campaigns, emergency cooling centers. Every one of these measures can reduce risk. Every one can save lives. The challenge is implementing them before conditions become more severe. Because unlike many natural disasters, extreme heat often provides fewer visual warnings. There are no towering storm clouds announcing its arrival. No dramatic radar images capturing public attention. Heat creeps forward quietly, patiently, often unnoticed until hospitals begin filling and emergency services come under pressure. That silence is what makes it so dangerous. And it is why scientists continue sounding the alarm. Not because humanity is powerless, but because preparation requires awareness. The future of extreme heat will not be decided solely by the atmosphere. It will also be decided by infrastructure, planning, technology, and public understanding. The question is whether societies can adapt quickly enough. Because as temperatures rise and humid heat becomes more common, one reality is becoming impossible to ignore. The greatest challenge may not be surviving the heat itself. For thousands of years, humanity has survived in some of the harshest environments on Earth. We've crossed deserts where temperatures soared above 120 degrees Fahrenheit. We've built cities in tropical jungles, arid plains, and scorching coastlines. Time and again, people adapted to heat through ingenuity, resilience, and determination. That history has created a powerful belief. The belief that humans can survive almost any climate if we simply prepare well enough. But the science we've explored today reveals a sobering reality. Our ability to survive heat is not unlimited. The human body operates within strict biological boundaries. It depends on a delicate balance between internal heat production and external heat loss. As long as sweat can evaporate, that balance can usually be maintained. But when heat and humidity combine in the wrong way, the body's greatest defense begins to fail. And once that happens, survival becomes a matter of time. What makes this discovery so unsettling is that the conditions scientists once considered almost impossible are no longer confined to theory. Dangerous combinations of heat and humidity have already appeared in some of the world's most populated regions. Deadly heat waves have claimed tens of thousands of lives. Cities like Karachi have shown how quickly extreme heat can overwhelm both people and infrastructure. The future remains uncertain. Scientists cannot predict exactly when or where the next catastrophic heat event will occur. But the trend is becoming increasingly difficult to ignore. The world is warming. Humid heat is becoming more intense in many regions. And the margin between survivable and unsurvivable conditions may be smaller than humanity once believed. Perhaps the most important lesson is that unlivable heat is not just a climate story. It's a human story. It's about the limits of our bodies, the resilience of our communities, and the choices societies make in the decades ahead. Because the question facing humanity is no longer whether extreme heat can become deadly. We already know it can. The real question is far more profound. What happens when parts of our planet become so hot and humid that the human body can no longer survive without technological protection? The answer may determine where billions of people can live, work, and thrive in the future. And for the first time in human history, that answer is no longer a distant possibility. It's a challenge that may already be beginning. It may be ensuring that the systems we depend on to survive it never fail when we need them most.